Right, here's the Unit 3, Constant Acceleration, Part 2. All right, let's see what we got here. Car initially at rest. That means that the initial velocity is 0, right? Accelerates at a constant rate, so this is the acceleration for 6 seconds, and that's a time. How fast will the car be traveling at 6 seconds? Make a velocity versus time graph for this situation. Okay, so velocity versus time. So the initial velocity is 0. This happens for 6 seconds, so 1, 2, 3, 4, 5, 6. That scale will do fine. And the acceleration, which is the slope of velocity versus time. So the slope of this is 4. Every 1 second that goes by, this goes up by 4 meters per second. If you're looking at that going, hey, that's a slope of 1. Nope, not if you scale this by 4. It's not. So I'm going to scale this by 4s. 4, 8, 12, 16, 20, 24, 30, etc. And I should stop there because it says it only happens for 6 seconds. So how fast will the car be going at 6 seconds? It's going to be going, call this the final velocity, 24 meters per second. Now look, if you make this graph very carefully, you can just look at that and read it out of the graph. But please understand, you should have your kinematics equations sitting right next to you here. And, excuse me, if you know these 3 things, if you make a little list, check it twice, then you should see that we have 4 meters per second squared. That's the acceleration. The initial velocity is 0. The time is 6. So we've got the stuff that we need. We could just read that out of our graph here, but you could also do it this way. So just real quick here, which equation would it be? Looking for that, that's going to be your VF equals AT plus VI. So either way, it's 24 meters per second. What's the distance traveled from 0 to 6? Okay, 2 ways to do that. You could either know that the area here, the slope of this, slope is the acceleration, and the area is the displacement. And here, since this thing's only going forward, distance traveled and displacement are the same since it never turns around and it's only going forward. So, what's the area of that triangle? 1/2 base times height. Or you could set this up, I've already got it set up right here, and go delta x is equal to 1/2 AT squared plus VIT. And that, not surprisingly, also gives you 72. So either one of those ways is fine. If you're thinking to yourself, oh yeah, I'm totally like down with this equation way, I like that, I'm just doing the algebra, you still need to be able to make this graph. So even if you don't answer the questions that way, you still need to know how to do that. All right. A tailback initially running at a velocity of 5 meters per second, that's my initial velocity, slows down at a uniform rate of 0.25 meters per second squared. Meters per second squared. This is an acceleration, and if we're slowing down, then that's going to have to be negative. Make a velocity versus time graph for this situation. So let's see, if we went 1, 2, 3, 4, if we made this 5 right here, what does this mean? This means that for every 1 second that goes by, the velocity decreases by 0.25, decreases by a quarter. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So after 4 seconds go by, it would go down by a whole 1, right? So however you want to plot out your points here. Do I have a straight edge around here somewhere? I think I did. My pile of papers just keeps getting bigger. So I should clean it up sometime. Well, let's freehand this. I think I can do all right there. That's all right. Good enough. Okay. How fast will he be running after going an additional 10 meters? So that's not this, right? That's 10 seconds. So I think we need to set up, if you're thinking like, well, what is that to the graph? How fast will he be running after going an additional 10 meters? That would be an area of 10 here, which would be kind of tricky to figure out how far over you would have to go. Because if you go over 2, that's like almost 10. But there's that little piece missing, so how much more do you have to go over between before this little like sliver is enough to make that up? Who knows? So I think I better do this like this style. And see what we know. How fast will he be running? So I'm looking for this. I know his initial velocity is 5. And the acceleration is negative 0.25. And, excuse me, 10 meters is this. So that looks like I want the Vf squared equals Vi squared plus 2a delta x. So Vf squared is equal to 5 squared plus 2 times negative 0.25 times 10. And I'll figure out what that is and then take the square root of it. At 4.47, I'm going to go ahead and round that to 4.5 meters per second. That makes sense for where we were here, right? About 4.5, a little bit lower than that. So yeah, that's about where we were looking on that graph. But couldn't really figure that out from the graph so easily. How much time passes before he stops? Well, I can't get that from the graph, although you might notice that 2.5 right here, it's like I'm halfway down. Looks like it's going to be 20 seconds. You could also think about if you're taking a quarter, like minus 0.25 off of this for every second that goes by, then 4 seconds is going to take off a whole, and then another 4, and then another so on and so on. So 20 seconds is looking pretty good. If that's all too magic for you, if you think you wouldn't recognize those things, of course you can just do this. Now, I don't have the 10 meters in play anymore. Like, that was a special, like, how fast will he be running after going an additional 10 meters. This is how much time passes before he stops. So what do I know? That's still that. He still started at that. If he's coming to a stop, then that's 0. And I've got 3 things there. I want to know what the time is. So that's this equation. And sure enough, do a little bit of algebra, get 20 seconds. How far does he run before stopping? So that's the same information as this, but we want the delta x. So I could use this time that I have here now, but don't necessarily need it, because I could use this equation again. So VF squared, VI squared, plus 2A delta x. That's 50 meters, I believe. Just gonna check my work here real quick, make sure I'm not telling you anything that's not true. Yep. There it is there. Sorry if I was off the page for a minute. All right. I think I got a little lazy here. I shouldn't do that. That's bad example setting. I'd like you to always write down all 5 of them. I was kind of anticipating what I was going to do there. That's a good habit to write down all 5. In here we would have had our delta x, but we didn't need it for that part. All right. Number 3. Plane starts from rest on a runway, ready to take off. At time 0, plane starts accelerating. That's the acceleration. The plane leaves the ground after traveling a distance of 200 meters. And it starts from rest. Watch out for that. It starts from rest. Okay, so velocity versus time graph. It starts from rest, and the slope, right, that's the acceleration, is the slope of this, is 5. So I'm just going to do 2, 3, 4, 5. The same thing that we did. Oh, maybe it was in part 1 of the review. But I'm just going to scale it by 5s here, because that makes this super easy to do. And get a nice graph that just goes right through like that. Great. Write the equation that goes with your graph. Okay? So I'm thinking y equals mx plus b, but I'm not going to write those letters. Right? Instead of y, this is v equals the slope of this so that's y equals m and then x plus b is 0. All right. How much time passes before liftoff? Now, I made the graph go at 10, but that doesn't necessarily mean that it has to go that far before we get our displacement of 200. So I think I would probably go ahead and do this. Okay, so what do I know? I know this is 5. I know it starts from 0, from rest. Final velocity, I don't know how fast it's going. Oh, it looks like that's going to happen in the next part. The delta x is 200, and I want the time. So that looks like it's this equation. So that's gone. So let's see. Just need to do a little algebra there. Should get about that the time is 8.1 seconds. I have 8.944 on my calculator. I round that to 8.9. How fast is it going? So let's see, that would be a different equation. That's one with no time in it. That is my VF squared equals VI squared plus 2A delta X. So VF, that's what I'm looking for. VI is 0 plus 2A delta X. Going about 44.7 meters per second. That's about 100 miles an hour. Seems about right for a plane. Planes go faster than that, but right at takeoff, I think that's probably pretty close. Depends on the plane, of course. Okay, let's see what we have here. Two cars are heading toward each other, as shown in the diagram below. This one. Car A starts from an initial velocity of 2 meters per second and accelerates east, so the acceleration is also positive. This is like the positive direction here. That would be the negative direction. Accelerates east at 1 meter per second All right. Car B starts 200 meters east. Okay, so it starts like over here, and it has an initial velocity this way, so west, that's a negative direction, so I need to make that negative, and accelerates east, but its acceleration is positive, which means its acceleration is going to be slowing it down, like fighting against it, of positive 2. Okay. Make velocity versus time graphs for each car. So for car A, my initial velocity is 2, and it's going up by 1 every second. So that's if I'm scaling this by 2s. Maybe I should have just made it 2. Well, whatever. So if this is going up by 2s, and this is just ticking off seconds, 1 at a time. Then after 1 second, it would be 3, 4, 5, 6, and so on. Like that. For car B, it starts with a velocity of -20, so I think that this graph is kind of messed up for my purposes. I think really I'd like the time axis to be up here. Right, like that to be 0. So sorry about that. So if that's 0, and then I want to get to -20, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So that's -20, and it goes up by 2 every second. All right, I write the equation that goes with each graph. So this one, the velocity, I'm going to put a little a there so I know which one I'm talking about. So I'm thinking y equals m x plus b. Those numbers have to have the units on them. That's meters per second squared, that's meters per second. And then the velocity for B, that's my y equals m x plus b. You could just write -20 if you want. You don't have to do that plus negative thing there. Write an expression for the distance that each car has traveled after time t has passed. Okay. So this is basically the when you have to do this, write a position equation, position, as a function of time. We know that these are these curved things, right? Like going back to review, where is it? So many papers. Like there's an example. We know that this is some kind of parabola, and this is going to be something about position is equal to like some kind of t squared, some kind of equation for a parabola. Which equation is that? This, we should be thinking that delta x is equal to 1/2 at squared plus vi t. Now, if you want to actually know what the position is, then you have to start with, that's really, well, whatever. Delta whatever is x final minus x initial, right? Delta something is final something minus initial something. So if you want to know where this thing is, we just need to take that initial position and add it over to here. And that will tell you the actual location of this thing at time t seconds. So it looks really identical to this kinematics equation, but we like to have that over here so we can actually know what is the location. So I'm going to use this for each of these now. So the position x of car A is 1/2 a t squared plus initial velocity is 2 vi t plus the starting position. But this one, if this is like starting position 0 and this is 200 over here, this one started at position 0. So I didn't have to worry about that. Well, I guess I did have to worry about it. It just turned out it was 0 where it started. Okay? Position for B, 1/2 a t squared plus initial velocity is -20 t plus the initial position. This one, not 0. If this is position 0, then this is position 200. All right. Now, when are the cars at the same position? They will be at the same position when their combined distance traveled is 200 meters. That, you could do it that way. We kind of did here, write an expression for, we really did it with position here, which I think is a better way to do that. So when are the cars at the same position? Well, I have position functions for these. So here, they're going to be at the same position when these two things are equal to each other. So I'm going to rewrite these, set them equal to each other, and ditch my units so it's a little cleaner. So 1/2 times 1, that is 1/2 t squared plus 2t. And then this one, oh, one of these had an acceleration of 2, didn't it? This one did. Sorry, that's wrong. That should be a 2 right there. My bad. All right, so 1/2 times 2 is 1 t squared minus 20t plus 200. All right, I need to get everything onto one side because my algebra teacher told me to. So t squared minus 1/2 a t squared is 1/2 a t squared. Minus 20 minus 2t is minus 22t plus 200. And I don't feel like using the quadratic formula. I bet you don't either. So I'm going to go ahead and graph this. So I got 1/2 t squared minus 22t plus 200. And before I hit graph, I'm going to just check to see what my window is set at. So the x values here are going to be time. So time 0 to 20, sure. That might be more time than what I need to see where they're going to cross, but that's fine. X scale, that's just how often we make the little tick marks. That should be fine. And then the positions 0 to 100, I think I really need to look at 0 to 200. That's all the possible positions that could be going on here. All right, I think I'm ready to graph. And there is where it crosses. So I want to figure out what the 0 is of this equation. You can do a little game with the arrows. I didn't really count out there, but it definitely looks like it's in between 10 and 20, doesn't it? So 10 and 20, like 12.8. And where do they collide? Well, I got this 12.8 now. I can plug that into this equation and plug it into this equation. And either one of those will give me the right answer, but it's a nice check to do it with both of them. So you can see that you get the right answer both ways. So the position of car A would be 1/2, here's my time, 12.8 squared plus 2 times 12.8. Let's plug in the 12.8 into this. And then B, basically I'm plugging it into this, right? So 12.8 squared minus 20 times 12.8 plus 200. All right, I'm going to do both of those just to see that I did it right. 1/2 times 12.8 squared plus 2 times 12.8. That's about 107.5 meters. Now, I did round this number, so I'm not expecting to get exactly the same thing, but it should be, certainly like within a meter or something. The answer shouldn't be that different because of my rounding. And doing it this way, 12.8 squared minus 20 times 12.8 plus 200, 107.8. So if you're wondering, well, which one would be the right answer on the test, Mr. McGrath, either one, or anything in between. All good. Alrighty.